If you look at your essay responses, when I get to this level, I have 3 grades. 80%, 90%, 100%. You get an 80% in an essay question, you might as well failed it. When I ask you to tell me how you make oil, and you regurgitate a kerogen question, that's not answering the question. When you make oil, you start off by depositing organic rich sediment in the right type of environment. You take that organic rich sediment, you start producing it from a solid into a liquid. That's called maturation. That's called cracking. You tell me how it works. And then you tell me how you get that oil from the source rock into the reservoir. And it goes through 2 stages, primary and secondary migration. When you get a question that's an essay, and I say, give me a page, I don't want to see this much stuff. I get that at the 100 level all the time. At the 300 level, you guys are just ignoring your responsibilities. If this happens again, I'm not going to be giving you 80% when you fail. You're going to be getting zeros. Serious stuff. Now, for those of you about to graduate, it doesn't matter. But there's a couple people in this class that are here for a couple more years. You guys need to start giving what we want, not what you think is an acceptable answer. All right, everyone clear on that? I'm off my soapbox now. I'll leave the camera on because we'll go over the answers. But although these grades look pretty good, they're not nearly as good as they should be. As I said, everybody should be in the 100% range. You can sit down and mind the field of view? All right, have a seat. All right. Going over this. Part 1, acronyms. By the way, I never know if it's acronyms or analogs or whatever the proper term is, but it's just meaning symbols. Some of these you've seen before, and you should have got these easily. TDS, total dissolved salts. Although I took total dissolved solids as well, although that's kind of not exactly what we're looking for. API, American Petroleum Institute. SP, spontaneous or self-potential. Either would be acceptable. RW, not something we've heard before. Resistivity of formation water. Okay, that was kind of buried in one of those slides, but I expect you guys to be looking at those things. NSO, you've seen that before. Nitrogen, sulfur, oxygen. That had to do with the composition of organic compounds. Definitions. For the most part, this was okay in terms of how it was done. Although, for those of you that said crossover, crossover is not when 2 logs cross over. Crossover is when the density and the neutron logs cross over, and it's important because it shows you where the potential is for natural gas. And by the way, if you said that, you got most of the credit. But simply saying they cross over is insufficient. Which one goes left, which one goes right, that's important. So if you don't give me that, then you're not answering the question entirely, okay? The petroleum window. The petroleum window is actually associated with temperature. Now, while you normally see people talking about it associated with depth, you have to understand that's based upon a consistent or average geothermal gradient. It's the temperature at which liquid petroleum is produced from maturation of solid organic material. Actually, you know what? That would have been a good thing to ask and add into your how oil works essay question. Short answer questions. Look at your test. If you see the word compare circled, if you see it circled once in red, that's because you're the first person that happened to do it. If towards the end it looks like the pen has gone through the paper and actually through all the papers, because I was getting tired of circling that, compare and contrast means tell me what's similar, what's different. And by the way, for those of you, again, this is primarily for people that are here for another couple years or so, if you did the compare and contrast 3 types of kerogen question, and you listed the 3 types of kerogen, like I did on the slide for you, that's not answering the question. Because if you look at the question, it says actually answer it in a paragraph. You know what a paragraph is, right? A written paragraph. Listing things is not answering the question, all right? And again, if you're going to play the game right, at this level, you guys are about to graduate, you need to give us what we're asking for. And if you're not, well, look, put it this way. If you take this into a career field, you're going to get a couple talking to by your manager, and if you don't actually give them what they want, you're not going to be working there anymore. Now, we can't fire you here, but we can certainly make your life difficult as much as we can around here, by cutting you off in the coffee. That's it. No more coffee in this class. No more cookies in this class. There you go. There's your penalty. Problem is I like coffee and cookies, so I can't do that. Comparing, contrasting, actually I'm saying this now because just about everybody who answered these questions had the same comments, okay? So if you did the 3 types of kerogen question, what I wanted to see was the geochemistry. What's the differences between them? What's the differences in terms of where they're sourced? And ultimately what their composition is, okay? So that's what I'm looking for. Compare and contrast stratigraphic and structural traps. What I was looking for here, and if you see the term that says it's a timing issue, what I'm trying to say is that stratigraphic traps are largely depositional in nature. They are formed at the time the sediments are being put down. Structural traps are secondary, post-depositional. That's the major differences between them. And once again, if all you did was just list the different types of traps, that's not comparing and contrasting. They are similar because they're means by which petroleum can be trapped. And a couple people, just to clarify one thing here, a couple people actually said that stratigraphic traps have porosity that controls things. Structural traps have something else. It's all controlled by the same thing. Porosity is what is controlling how much oil and gas you can have within a deposit. All right? That doesn't change. That's consistent. It's the nature of what is restricting the oil from migrating out of that area. Comparing and contrasting gamma ray and neutron logs, the comparison, they both deal with radioactivity. Gamma ray logs are passive. You record how much radioactivity is being emitted by the rocks. Neutron is active. You emit radiation and measure the response. That was the key differences between them. And once again, going into talking about how they actually tell you different things is important too, but those are the key differences I'm looking for. All right, now I've already gone my bandwagon in terms of how oil forms and stuff like that. Now allow me to do the same thing for the rest of you that answered question number 2. Why do we have to use multiple logs? The key reason for this is that electric or wireline logs do not tell you anything about the physical nature of the rocks. Physical sampling is still by far the most useful way, the only way of interpreting, quote, the subsurface geology. By the way, I wasn't asking you for petroleum, I was asking you about geology. How do you determine the geology below the surface? If you had a core, you would know what it was. You don't have cores in every situation, therefore you need wireline logs. It's all abstract data. You have to interpret it. And then that's where you get into the hows you do it. You do it by combining logs because resistivity tells you one thing, SP tells you something else. Look out for the ringers. Most of you got that aspect of things. But the real key concept here is you need to do this because we have no physical evidence about what the rocks are actually going to be like. You know, there are people that work in the petroleum industry, I hate to say this, have never seen a rock, at least in the area they've been working in. They have never seen the rock that they are interpreting, and yet they'll tell you everything you ever want to know about depositional environments, petroleum potential, porosity, and stuff like that. And if you showed them a rock and gave it to them on their desk, they say, "What is this?" And you say, "That's the rock you've been studying and finding oil out of for the last 20 years." And they'll go, "Really? Cool." And they'll turn it into a paperweight. All right? All right, so Dems the brakes, all right? You got your grades back, and as I said, for the most part, everybody's okay shape. The average is okay and stuff, but I don't want to see that at this level. I want to actually be impressed. I want to see people giving me stuff that makes me go, "Oh my God, I want to be in tears." I actually want to have to get up and get a tissue paper to blow my nose because I've been moved. I was blowing my nose an awful lot last night because I've just been really snotty. This trip, I don't know what it was. I was just kind of allergies. And that's not the type of stuff I'm looking for, okay? I'm looking for other stuff. Anyway, that being done, that's one down. The next test is also going to be an in-class test, and I'm expecting better stuff from you. What do you want?
What's the next one?
Final. All right, there's only 2 tests. I mean, that when you take this into account with Connor's stuff, he has 2 tests, I have 2 tests. That's 4 tests. That's more than enough for a class like this. So, what?
You did a core addition job, and you owe me 2 more points.
Okay. If I owe you 10 more points, that's fine. That's actually hard to believe. I owe you 10 more points on that. I'll have
But you wanted the short answer, or worth 20, and you gave me 10. And, but you said good, and you don't have any marks on this. so I assume you wouldn't give me full points.
I don't know.
That's the subject.
As I said, I seem to have had to go downstairs to get my own creamer today. Maybe that's the penalty. Whatever. All right, that being said, now, getting back to where we stand on this, okay? Today we're going to be talking about fence post diagrams. That's the last part of the lab exercise you got going for. Now, I know most of you have done fence post diagrams and stratigraphy. That's great. Most of the stuff you've done in that class will apply to this as well. However, I want everyone to be aware of how to do this and how to make them more relevant to the petroleum industry, and that means we're going to go through an exercise. A little bit later on, after we go through a very brief slideshow, I'm going to distribute a bit of an exercise. I'm going to ask you to break up into 6 groups, 2 per table. So 3, Connor, if you move over there, there's 3. 4, 3, you get the idea, right? Just kind of concentrate on that. I'm going to give you this and we're going to work on it together so you know how to actually set this up. And for those of you that did this in stratigraphy, the concept is pretty well the same, although I understand Dr. Clark uses an overhead projector, right, for doing this. Well, I don't have an overhead projector, and as best as I know, most of ours have melted, so this means you can do it at home without having to worry about having an overhead projector. It's the same basic concept, okay? Then this will be the last part you have to do for this exercise. This lab that you've been working on for the last couple of weeks is due a week. Tomorrow, is it? I think it's a week tomorrow at 5 o'clock, something like that. Everything's got to be done by that time, including any renovations or revisions you have to your gamma ray sections. SPs are done. All right? Okay, with that, can you kill the camera and we'll get started with the lecture today. By the way, while this is... that's going to turn the lights off here. I actually had some win over on Friday. I got in touch with the person who is the mud logger, and we had a nice little interview on Skype. Had it recorded, used a new type of software. Had it making the movie. I had to leave it on over the weekend to make the movie. It came back and it filled up my computer. I had 60 gigabytes on my computer and it filled it up, which leads me to believe that the software maybe isn't all that good. So I deleted the stuff I thought I didn't need, and what I did was I deleted all of his video component. So you see me on my side. My side's fine. I'm going like, yes, so Jeff, would you mind telling us what's going on? And then you hear Jeff talking and there's no picture. So I'm trying to figure out how to deal with this. I think we may have to redo the video. So I'm going to give you this opportunity. If anybody has any questions that you would like to ask someone who's had experience as a mud logger, that's the people that actually work on a rig processing the samples, or someone who's worked for Schlumberger doing electric wire line interpretations like this, then feel free to email me by 5 o'clock today. I'm going to try and call them again tonight and do it again. This time I'm going to make sure that I use a different type of software, okay? So if you have questions, then email them to me and I will do my best to ask them on your behalf, okay? And I'll try to get that thing sorted out as soon as possible. As I said, I thought I was going to have that lecture online today, but I mean, 60 gigabytes for a 30-minute interview? I mean, so most of the 60-minute videos I do for mineralogy are like, what, a gigabyte or 2 at most. So I don't get that at all. So weird science. All right, today, very quickly, fence post diagrams. Has anybody not done a fence post diagram? All right, so you guys are the... You know that 10% I took off your... I'm sure was anticipating you giving me a rough time today, so we'll call it kosher or quits now, okay? If you haven't had stratigraphy yet, this will be important information, and make sure that when you do stratigraphy with Dr. Clark, you listen to her methodology, okay? Because everybody has their own way of doing things. So what I'm about to tell you might work in some places, but hers is probably best for what she wants to do. Last time we met, we were talking about isopac and topo formation maps. Very quickly, just to remind you that the light's blinking. It's kind of weird. Just to remind you what they were. I've got 2 images here as reminder images. Well, first of all, the definitions. Isopac maps are basically contour maps that show you equal thickness in rock layers. They're very, very useful in petroleum geology for looking at potential areas where you can have thick plays or thick potential reservoir rocks. So you're going to have an exercise doing this on the tops and bottom of the formations that you did on your sections. We also talked about top of formation maps, and those just more or less give you an idea of the top, what the elevation and the top of the formations are at. Now for these maps, the TOF maps, those are usually corrected to take out the top surface out of the picture, because basically what you want to do is get an idea of the depositional profiling that was around at the time the formation was being deposited. So you want to take out the issue with surface topography, and as I explained in the lab, I didn't do that this time around, so we're just going to ignore that component of it. But this is what you get if you're doing a proper isopac map. You get basic formation thicknesses. It allows you to look for local highs and lows. And a couple of people asked me this afterwards, does it help you to find things like salt diapirs? Absolutely. But of course, if you need an isopac map to determine where salt diapir is, you're not playing the game right anyway, because I mean, those are the things that you've already drilled. This more is useful for things like looking for reefs that might be in carbonate deposits or shoals. I've seen really nice isopac maps and topo formation maps where you can actually see barrier island complexes that are preserved, including their orientation. And again, looking for oil, you need to know where these positive things are. Okay. Topo formation maps, as we discussed, more or less give you an idea of what the depositional surface was like. Your topo formation map is not going to be particularly useful because, again, it was kind of not put together with me thinking about what the final product was going to be. So don't expect miracles on that. But realistically, you seldom get things that give you really nice stuff like this up dip kind of thinning in terms of this particular formation. Now, with that being said, here's what we're going to be doing today. Again, it's going to be a short lecture. I wanted to have lots of time for us to actually play around with this as an example, so everyone knows how this works. Okay. So first of all, what fence post diagrams are. I'm going to give you some examples of fence post diagrams and how to make them. Okay, so very quickly running through this, since the vast majority of you have already seen these before. A fence post diagram is essentially a 3D rendering of geology over a regional area. Okay, so the idea now is, and you'll see this in a second, if you've got a cross-section gives you a slice. Ideally what you want to do is get a feel for what the geology is like over a larger area. But the problem is when you're looking over a three-dimensional area, very quickly it can get really cloudy and murky when you've got correlation lines all over. Fence post diagrams allow you to pinpoint certain places where you can tie in sections to give you a three-dimensional picture of the subsurface. Now, the issue is going to be this. In petroleum geology, you have to take your data from the sections and wells you already have. So you don't have the ability to kind of vary where things come from. The only way you can do this is by orienting things so that you can see things most clearly. So, as this thing says here, orientation for fence post diagrams, at least for effective communication of data, is absolutely critical. And you have to sit there and tweak it around. Don't just go for the first fit. You need to make sure that you can see as much as possible. In some cases, you may be forced to draw a diagram where the north arrow is pointed directly towards you. And I'll show you what I mean by this in just a few minutes, okay? And as the other types of maps, you can do this on surface exposures or subsurface strata. And you need, and this is the one thing that is kind of unfortunate, you need to minimize the detail as much as possible here. Because you've got to, if you're dealing with something that's over a large area, your sections that might be this long in terms of the cross sections may be reduced to something this big in order to fit them on a piece of paper. So that means you reduce your detail just basically down to basic formations. I'll show you what I mean by that in a second as well. Okay. Now, again, why do we do this? Because while a two-dimensional cross-section like this, and this is actually quite nice, this is a well log tied into a seismic section, really very pretty actually, I like the way they did this, shows you something in two-dimensional slices. What it doesn't allow you to do is ask the question, what's here? Or what's in the plane of the board? But if you have some sort of means by which to show something over a larger three-dimensional area, you can start to target specific things in areas that the cross-sections you did don't actually cut through. Case in point, this is a god-awful diagram, okay? I don't expect you to get much out of this. What it is, it's a three-dimensional seismic line. You can see one going off in this direction, one coming off in this direction. So basically you're looking at a wedge like this. There's the base. That's the top. We'll talk about this starting Wednesday's class. That's a time slice showing you, again, certain contacts. But what this is showing you now is a pattern of wells that penetrate over a certain area where they bottom out according to different layers, and these things are color-coded to the layers you're dealing with. Now, that's not an effective way for you to understand the geology, because you and I are not working in the petroleum field in this area, and this means absolutely nothing to us. But if you are someone who is, say, trying to develop or enhance a field, then knowing the pattern where these things are in three-dimensional space really does allow you to start thinking about maybe, kind of producing this area or in this area. And look at the way they have this projected through a horizontal plane, so you get an idea of where things are horizontally in this direction, but also depth in this direction. So these things are pretty useful, and computers do this all the time. This is one of my fence post diagrams that I did for my PhD study, and what this is showing you is just sedimentary lithology. And this is the type of thing that I would recommend that anybody in petroleum geology gets used to. The black you see here is mud or shales. The sandstone pattern you can see here is the sandstone pattern. The dashes are carbonates, and well, you get the idea. It's a standard symbol that we would use for any type of lithology. Now, what you're looking at is a pattern of sedimentary sections, surface sections, that are scattered over an area of about 200 square kilometers, indicated by A, B, C, Ds, etc. Now, the real trick to doing this is coming up with an orientation that allows you to see things as much as possible without causing you the grief of having things cut through stuff. Now, you can still see here that I was forced to kind of go through in this direction, cutting off this part through here. That doesn't really matter too much, because the fact of the matter is that's a small amount. The same way as that's been cut off. But what you can start to see now are patterns of mud sand changes as you go from one part of the section or the area to another. Now, when you do your fence post diagrams, when it comes time to actually looking at your formations, I would recommend that what you do is come up with a simple color pattern that mimics the sections that you did previously. Use the same colors as before. Everything should be able to be tied in together. So colors rather than worrying about any squiggly things. And use strip maps. A single column with no differences in terms of sediment thickness. And for those of you who had sedimentology before, don't start trying to worry about whether you got shales or mudstones. Just columns. It's a lot easier. Okay? Position them and then start correlating them like this in a way that you're not going to have problems cutting through things. This is the type of thing that Dr. Clark likes you to do in stratigraphy. And notice this is really quite nice. You can see the color bands through here. What you have here is, instead of the actual columns, what you have is just a line where things bend around. This is kind of effective in some ways, but I'm going to ask you for consistency to use the column approach, because the way I'm going to show you how to do this kind of has to have you doing the columns and rotating them around. Okay? So notice here, however, that the color very clearly can be seen all over the place. Once again, minimal cutting through. This orientation is really quite a good one. And look where the north direction is. This time coming towards you. Okay? And then that brings us now to the exercise. How do you go about making a fence post diagram that has a good orientation, that is effective at communicating, and yet will not drive you insane? There are easy ways of doing this, and I suppose there are hard ways of doing it. I'm going to show you the way I do it. If you prefer doing it the stratigraphy way, that is fine. But remember, you're going to be evaluated on the orientation that you do. Now, this is a sample exercise. What I would like you to do is divide yourself up into 6 groups. And turn the lights on. That's basically all we have to do today for the slideshow. And it would be a good idea for you to be in groups of 3 or 4, not too many in a group, okay? Simply because I want you all to be able to position yourself and play around with this. Okay, the real thing about doing fence post diagrams is that you have to get a perspective, an orientation that is the correct one given the layout of the land. And you're really restricted in how this works based upon the actual map layout. So in the example that you have here, the layout is such that you have a series of wells that are aligned in approximately this orientation, almost in a cross fashion. All right, so technically you'd have 2 cross sections that more or less would do this. And if you were doing this as an exercise, then of course you would have section A, section B, or for the exercise that you did in the lab, you'd have your northeast, southwest, southwest, northeast sections, etc. Now, in this case, what you want to do is come up with a way which could illustrate the three-dimensional relationships of these wells. What you have to do is somehow go from this orientation, which is a map view with the north arrow oriented this way, to something that is more aligned in three-dimensional or block diagram fashion, like so. Now the trick to note here is that when you're looking at wells that are located here, 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 etc., on a perspective diagram like this, they are going to be related to one another in kind of like a squished or a perspective view. So that might be the orientation that you get in a block diagram relative to the map view. North, in this case, would be in this direction, like so. Now, the real beauty about fence post diagrams is, of course, that once you have some sections, you can start to get an idea of how they are related in three-dimensional space. Let's push this one over to the side here. So if this happens to be formation A, say the Waikato limestone, and the Waikato limestone is over here, you can look at the perspective this direction, then in this direction, like so. Okay, so the trick now is how do you go from this to this? Now this is the way that I would do it. Okay, now the exercise that we're going to be doing together, you have three different components. The first component is the map, which we just more or less looked at on the whiteboard. The second component is a schematic log. This is an SP resistivity log, which has the formations mapped out on them. And then you have a series of small little strip sections. Now let's start off with how you go from the log to the strip sections. This particular log, if you look from the top, goes from the so-called Kelly Formation through the Hurd Formation to the Charles Formation, etc., all the way down. And you'll notice that the formations have been spotted based upon the kicks on the SP character. What you want to do is condense this particular log into something that is smaller that would fit on a fence post diagram. Remember, in order to make this work, you've got to minimize things. You do not care about the nature of the log responses. All you want to know is the relative thickness of each of those formations. Now what I did was, I more or less took this log and identified where the different sections were in a strip fashion. Then I photo reduced it down using a photocopier. So this is the result of my photo reductions. That's the same log. Proportionally, each of those formations is the same as the larger log to the side here, except it's just easier to work with. Now we have 7 logs in this exercise, and those 7 logs have been more or less done for you here now. Okay? And the purpose for what you're doing on your larger project, you need to take all of the logs that you did for your 2 cross sections, that's a total of 9 separate wells, more or less photo reduce them down into small strips like so. And the easiest way of doing that is to more or less take a piece of paper as long as each of the logs, make strip maps by just simply putting the paper beside your logs and just marking where they are proportionally. Also mark down what the scale is. Now the trick here is if you draw everything to the same scale to start with, then are consistent in how you photo reduce things down, then the scale will go with you. So in other words, if you look here for this log, all right, that has a standard type of spacing that we had on the previous logs. The top of the strip map I have here has a very small scale on it. That's representing 200 feet. Now, as long as the scale is proportionally photo reduced and is consistent for all of these, I never have to worry about the scale again. Okay? So, job number 1, convert this into a series of strip maps, photo reduce them all down at the same scale. Now, once you do that, the next thing you have to do is to try and sort out the best orientation by which to organize your fence post diagrams. Now this is where you have to start getting tricky. It doesn't matter what the orientation is relative to space, because you want to find something where the sections are not going to more or less bump into one another or cover one another. Now the way I recommend doing this is to more or less look at the map at a very sharp angle. Say like this. Rotate the map field around until all of the well positions are more or less separated from one another. Now, in this situation here, this case, log number 5 here is clearly separated on its own, as is 6, as is 3, as is 2. But here you're going to see right at the edge, well number 4 and well number 3 overlap one another. So from this point of view,
4 would cover 3. This is not a good vantage point. If you rotate a little bit more like so, you'll see what you're doing is you're separating well number 3 from well number 4 in this orientation, but what's happening now is you're starting to overlap wells 3 and 2. This is not the easiest thing to do, trying to find an orientation that works in all different directions. So you have to rotate it around until you try and find something that looks like it might not be a bad vantage point. Now, this particular orientation here is not too bad. There is a bit of overlap here between logs number 1 and log number 7, but it's not too bad overall. In order to check your orientation, one thing you want to do is to also put the strip maps down on each of the well locations. Okay, so I'm going to reposition the camera here a little bit like this. If this is the orientation that we're going to be working on, about an angle like this, what you want to do is take each of your logs and position them so that they are parallel to the point of view that your perspective would be looking at. So well number 7 would be like this. Well number 5 would be like this, and all of a sudden I can see a problem because well number 3 and well number 5 actually overlap a lot more than I was expecting. So this is not going to work. There's 3, there's 4, there's 2. In fact, I didn't do very well at this at all because they're all overlapping in the middle area, okay? So that doesn't work well. Now, if you're good, what you can do is start rotating the paper to get a better vantage point, but always remember you've got to rotate your sections along to reflect the orientation that you're looking at. So if you rotate in this direction, all of your logs must rotate so that they're parallel to one another. Now this is where Dr. Clark's idea about using overhead has its advantages, because what you can do is you can project this onto a screen and then you can rotate the overhead transparency, and it's a lot easier because what you're doing is making this larger. Now clearly this is not going to work like this because the strips are larger than papers, and when you blow this up into a larger scale there's going to be separation. But it does give you an idea of the overall orientation that might work. So this is something you have to do individually. Try to find something that's going to give you the best separation, and if you can get something that looks like this, relatively speaking, where each log is separated a little bit from one another, like this, then you're more or less laughing, okay? So that's the next phase of things that you have to do, is get an orientation, some sort of perspective that is going to work for you, say like that. Okay, now once you get your perspective to work out well, and this is the perspective that I've sorted out on mine, okay? So my orientation looks something like this. Your north arrow in this case, and my vantage point is that way. What you want to do is now start laying out your sections that have already been pre-cut to some scale and are numbered to correspond to the section that you actually see here. You need to find what would be your datum. In other words, one of these boundaries has to be a fairly good datum. In this case, we're going to call it the bottom of the Fancher Formation. On this little strip map here, that's right there. Okay, so that's where I'm going to call my datum. So the Fancher Formation datum I'm going to put in a solid line. There's what it looks like for log number 3, log number 5. Now the easiest way of organizing things on this is on a piece of paper, whichever size you're going to be using, take your different logs and position them so that the base of the datum is going to be right at the point on the map where your log well locations are. Okay, so there's well number 5. I'm going to put the base of the Fancher Formation right at that point. So there to there. Now what this is allowing you to do is to define a horizontal plane. We're not going to keep this plane in our diagram when we're done with it. What we're going to do instead is just use this for laying things out. Alright, so there's the base of the Fancher. There. Number 6. Right there. Now again, I'm doing this on a whiteboard. You can do this on a piece of paper. This does not have to be on a vertical perspective. Although again, if you were doing this in stratigraphy with Dr. Clark, this is how a lot of people get their stuff organized. You can do this on paper or on a wall if you wish. Oops, the Fancher Formation is there. And lastly, number 7 is there. Okay, now as you can see from this is actually pretty good separation. None of the well logs actually correlate or overlap one another, so they're nicely separated from one another. Now notice you're going to lose the position where the wells are. It's not critical in this type of map to show them where they are. Make sure you have your north arrow in there. The other thing you want to do also is make sure that you have some sort of horizontal scale that is clearly determined based upon the separation of the wells. And now we need some sort of a vertical scale as well. Okay? That will be based upon what the sections were here. So in my section number 1, that represents 200 feet. So there's 200 feet from there to there. That would be 200 feet from here to there. A lot of people actually like to have both scales put together here now. So you have the vertical scale and the horizontal scale, which would be two totally different scales because you're dealing with two different things. You got your north arrow, you got your scales, you are lapping in terms of everything. Now at this point, you can get rid of that base line. That was only there to get us started. Everything from this point on now is going to be based upon correlations between each of the sections. And you are going to have to use a ruler to do this. I do not have a ruler big enough to do this right now, so I'm going to wing it. But you are going to do this properly. You also need to get an idea for which lines you want to do. Okay, you can't try and correlate everything, but there will be some obvious connections which are going to work best. For example, in this direction here, we can easily do these correlations like so. And again, you would be using a ruler. Actually, you know what I'm going to do? So this is easy for everybody to see. I'm going to use a different line for the datum. I'm going to use a red line for the datum. All right, and you know, we could go in that direction. I think I'm going to go in this direction to show you how to deal with things that are going to cut across different. Well, see here you have to actually start thinking about what the layout is going to be. You know, the best way of doing that might be actually to do it on the map here. Try to get a feel for which orientation